All right, now we'll do chapter 4. Now, I told you when we did chapter 2, so chapter 2 is kinematics in 1 dimension. Chapter 4 is kinematics in 2 dimensions. But, I mean, there's a lot more to this chapter than that. But basically, you know, kinematics in 2 dimensions is just twice times kinematics in 1 dimension. So it's nothing really new. However, we're going to pretty much concentrate most of the time on free fall, so it's even going to be less work than, and you'll see, than 2 times 1 dimension. But anyway, we'll see that. But I guess the important thing is, in order to understand chapter 4, you must have a superb understanding of chapter 2. So if you don't, go back and review chapter 2. You really have to know that very, very well. Okay, kinematics in 2 dimensions. To identify the acceleration vector for curvilinear motion. We've already done that. To compute 2-dimensional trajectories is new. Understand projectile motion. Okay, look. What we've done in the past, we said that this is free fall. Well, projectile motion is free fall, you know. If you throw something, remember I threw things around, I don't remember, a while ago. As soon as it leaves my hand, the only force acting on it is gravity, so it's free fall. Okay, so projectile motion is just another word for free fall. Okay, then we're going to do something different, relative motion. What's your motion relative to me? What's your motion relative to the speeding car, or whatever. That's a little bit different. Then we're going to do something different again. Then we're going to talk about circular motion, uniform circular motion. So we'll talk about circular things, angular acceleration, the kinematics, then we'll do non-circular motion. So this is a long chapter. I mean, in previous, you know, we're using the 4th edition of the textbook, right? In previous editions, this was not all in one chapter. But now, for whatever reason, they stuck it all together. So this is a long chapter. So just beware, okay? Just beware. All right. You've seen this before. So what's true about the direction of A and the direction of V? Well, remember, where do you get the direction? From a vector, you know? And, well, but hold it. I mean, delta t is always positive, right? So that doesn't really play a role. So the direction of delta v has to be the same as the direction of A, right? Because this is just positive. So we did that, right? And I just explained why. Okay? Now, remember I told you to see this before? I mean, you see it again? Well, now I'm proving myself, right? Okay. So we want to talk, so this is uniform circular motion. Uniform means constant speed, right? So, you know, I'm undergoing uniform circular motion. My speed is hopefully the same, right? But I'm going in a circle, you know? So uniform circular motion. Okay, so is the object accelerating at point A? Figure it out, and don't look at the answer until you figure it out. All right. Well, you know, acceleration is the change of velocity, right? So acceleration is the change in velocity over the change in time, yeah? And velocity has a magnitude and a direction. Well, is the direction changing there? Yep. So is it accelerating? Yep. All right? It's like, you know, it's like the steering wheel of a car, right? Okay, so it's accelerating. I mean, the speed is the same. That's why it's called uniform circular motion. But the direction is changing. So it is accelerating, all right? It is accelerating. All right, oh my gosh. You already did this. Do it again, please. You have to understand this. An object undergoes uniform circular motion as shown. Use vector subtraction to find the direction of the acceleration at point A. So let me give you a little hint. Okay, so we know that the direction of A is the direction of delta V. We just discussed that. And of course, delta V is V final minus V initial. So there you go. And we said, you can say that this is the direction of V after minus V before. Remember we did that? And so this is V before, this is V after. So just please do it. Do the vector subtraction. It's important to find the direction of the acceleration vector right at point A. Okay, just do it, right? So, so V after is this. So that's, or V final, whatever you want to call it, V final, okay? And then we want to, remember, this is the same thing as the direction of V after plus a negative V before. So V before is this, so that means negative V before is that, right? So that. So that's minus V initial, then you go from beginning to end, and you get something that's straight up, right? Straight up. Okay, so that's the direction of the acceleration for uniform circular motion. And you know, there's nothing special about point A. We could have done it anywhere, right? And so basically, anywhere you do this, you're going to see that the A vector always points towards the center of the circle. Okay, towards the center of the circle. Okay? So there you go. And we'll use that, you know, we'll use that later on when we talk about uniform circular motion. All right, next. I apologize because now I would typically do a demonstration, but it only works when you have a tile floor because you have to hear the balls hitting the floor. We are in a room where there's carpet, so it's not going to work. So I'm just going to describe it to you. Sorry. So here's the floor, and here's a bench, and I have this thing. It's called a projectile launcher, right? Projectile launcher because it launches projectiles. It shoots out balls, all right? So we have these, all right? That's all it does. So, so it shoots the ball, all right? Okay? And you won't use an ELAC with this remote. But anyway, sorry. Right? So all it does is, you know, you push the ball in here, there's a spring, then you let go and it shoots the ball, right? And it comes out horizontally, but then because of gravity it goes down. Okay? All right. So that's what it does. Now, what I'm going to do though, I'm going to have a little attachment. So here's a little attachment. So, all right. Okay, sorry about this. Okay, so this is an attachment. This is a metal ball, so there's a little magnet here, you know. Okay, so this ball, here's a spring, and there's a ball, right? Okay, so this ball comes flying out and smashes into this ball. So this ball, you know, does one of these things. And then this ball, after it hits that, this ball, I should have made them different. Yeah, hold on. Okay, so this ball hits this ball, sends it flying. This ball, it hits this ball, and then it just falls straight down. Okay, it just falls straight down. All right, okay, so this ball hits, all right? And you know, I mean, after they hit, the only force acting on it is gravity, right? All right, so here's what we want to do. Well, I should have just left that alone. All right, so this is what we want to do. So there are 3 settings on this. Slow, medium, fast. Okay? So if you just compress the spring a little bit, it's slow. You know, so it comes out slowly, right? When you compress it, you know, a little bit more, it comes out medium speed. When you compress it all the way, then it goes really, really fast. All right? Okay, so here's the question. What can you say about when will these 2 balls hit the floor? Different time or the same time? And again, I do it 3 different settings. So I mean, if we were really in 132, you know, the slow setting. Let's say here's the table, or here's the projectile launcher. So the slow setting, you know, the one goes straight down. The one go like this far. The medium, it go like this far. And the fast, it'd go all the way over here, you know. So again, the question is, which ball hits the ground first? This one, or do they hit at the same speed? And so, we have people vote and da-da-da. But anyway, the answer is, what do you think? After they hit, what's the only force acting on them? Gravity. And gravity acts the same on both balls, right? So they hit the floor at exactly the same time. I mean, if there were no such thing as gravity, this ball would just keep going straight, right? That's what happened, that's what would happen in deep outer space, right? But of course, this one wouldn't even fall. I don't want to talk about that. But all I'm saying is, it's the gravity that makes it go down like that, right? Gravity makes this fall, gravity makes that fall. And so gravity is the same on both, and so same time. Okay? And that's kind of cool, because again, this one always just falls, right? But this one, short, medium, or long. So it seems that this is kind of independent of this, right? This one goes short, medium, long. This one just falls. So it's like they're independent. They're independent. Like the x component here is completely independent of the y component, or the y component. It seems like they're independent. But the times are the same. The times are the same. So this is important. Picture's worth 1,000 words. The horizontal motion and the vertical motion are independent. Okay, they're connected to the time, right? They have the same time, but the horizontal and vertical motion are completely independent. All right? Now keep that in your head. Okay, now let's go through it. So now we want to talk about two-dimensional kinematics. All right. Well, what do? You just, this is what you hopefully have memorized by now, right? And so notice I put little x subscripts everywhere. I don't need to put them on the time because the time's the same, right? So this is just the three kinematic equations that you should know, but I have x's everywhere, right? X, 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 right? And now we have a y too, right? We have y dimension, x dimension. So I just put y's everywhere, So I have x, put a y, subscript y, 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 y. All right? So we just have the same equations, the same three equations. But this is in the x direction. This is in the y direction. So doing a two-dimensional kinematics problem is just the same as doing a one-dimensional kinematics problem. You just do it twice. So it's not so bad, right? There's really nothing new. Nothing new at all. But let's be a little lazy. What do you say? So we want to talk about free fall. Well, not yet. We'll get there in a minute, all right? So let's just consider a special case. So the special case is going to be, let's just say that we want ax to be 0 and ay not to be 0. And we could have done it the other way. We could have said that's not 0. We could have said that's 0, all right? Okay? So we only want the acceleration in one dimension. So for this, we don't want any acceleration in this dimension at all, constant velocity. But in this dimension, we want there to be acceleration, okay? So let's just do that, and you'll see why. Don't worry. All right, you'll see why. But by the way, wait a second. What's an, well, I don't know. Okay, so if we have ax is 0, that goes away. That goes away. That goes away, right? Oh, this is awesome, Okay, so there's our special case. We have ay just as some constant, and ax is 0. So everything in blue is going to goodbye, right? Right? Okay, so this is what we have left. Now look at, does this tell us anything new? Well, come on. Ax is 0. That means there's no change in the x direction. Well, isn't that what that says? Yeah, so we already knew that. That's just the same thing. So this is useless. I mean, it's not useless, but we already know this. As soon as we write down ax is 0, this is a given. This is a given. So why bother writing it? This is a waste of time. So goodbye, all right? Goodbye. So look, rather than having 6 equations, like you thought you were going to have to work with, now we just have 4. Oh, that's much nicer, right? All right, let's see. Okay, awesome. Now, let's do some math. That's all we have to do, okay? What we want to do now, before we get all excited, and before we start doing free fall, we want to get what's called a trajectory. Okay, the trajectory is y versus x. So that's what the dumb thing looks like, right? When you throw it, that's what it looks like, y versus x versus y, whatever you want, Okay? So let's do it. Let's do it. Okay. All right, so, we're just going to pretend we're going to throw something. I'm not going to throw it, right? We're going to throw something, okay? So we're going to do our pictorial representation, right? Of course, So we'll say this is the origin, but now we have 2 dimensions, right? Oh my gosh, a little bit more work, So x0, y0, v0, x, v0, y, t0. Yeah, you got to worry about that y. Okay, now, I don't know, I'm throwing it, right? And I don't know if it's going to, I don't know exactly where it's going to be, so I'll just put it up here. It could be down here, I don't know, whatever, So we'll call that point 1. So x1, y1, v1, x, v1, y, t1. Okay, wonderful. All right, now remember, this is a, good old chapter 2 problem times, 1 whatever. Okay, 1/3. So we get this is origin. So we have to say what all these things are, right? So we have to do that. So let's do that. All right, now we're going to be super lazy, right? So this is the origin. So I can say x0 equals y0 equals t0 equals 0. Isn't that nice? All right, and what can I say about the v0x? Well, remember, ax is 0. So let's say this. Let's just say that v0x equals v1x, right? Because they're the same, because nothing changes in this direction. Let's just call that vx. I have to keep writing the zeros and the ones, And it's constant, right? It's constant because ax is 0. Yeah, wonderful. Okay, all right, so now, but what's v0y? I don't know. Okay, but we don't know what v0y is, right? I mean, we're just trying to be super general, okay? So we don't know what v0y is. Okay, now we already said, I'm just going to repeat myself. We already said that ax is 0 and ay. Okay, what's ay? It's just, let's just call it a, and it's going to be some constant. Another constant, Not that one, something else, right? Okay, now let's go over here. So what's x1? I have no idea. What's y1? I have no idea. Okay, I know what v1x is. What's v1y? I have no idea, right? v1y, I have no idea. And I don't know what the time is either. Wow, a lot of unknowns, right? Okay, so see these 2 equations in the blue? Remember, we want to get an equation y versus x. So here's our x, here's our y. So we want to use those 2, okay? Let's use the one and let's use the x. Well, remember now, x initial is 0 because we said this was our origin. So all I'm going to have is x1 equals vxt1. Okay, so I'm going to have x1, that's my x final. Okay, vx is vx, right? The x initial is 0. Delta t is t final minus t initial. T initial was 0, so it's just t final, which is t1. Okay, so that's what I get from this. Right, I throw that away to just, that's what I get from that. Now remember, we want y versus x. So our plan is we're going to solve for t here and stick it in here. Then this equation is going to be y, it's going to have y's and x's, y versus x. So that's what we're going to do, all right? So therefore, t1 equals x1 over v1. All right? So now we're going to stick this thing in here. By the way, I think you're going to use this in one of your labs. So, all right? So we're deriving an equation. We're deriving an equation for the trajectory. So this is what you have to do. Okay? All right, so here we go, the one over here. Okay, y initial is 0, goodbye. This is t1. This is t1, right? It's supposed to have, okay. All right, let's do it. So we have y1. Okay, this is 0. All right. So I have y1 equals v 0y, v 0y t1 plus 1/2 a t1 squared. All right? Okay, now again, the whole purpose for this one is to solve for t1 so we can substitute it. So we're going to have v0y t1 x1 over v1, and here 1/2 a, that's squared. All right, great. So let's do it, and let's write it a nice way, you'll see. So I'm going to write this as write this as v0y over v1 times x1. And here, did I do it now? Okay, I did it that way. Plus, what did I do that way for? Yeah. Plus here, I'm going to have a 2v1 squared times x1 squared. Yeah, perfect. Okay? All right. And this is really supposed to be x. Remember we said v when x is vx? So just make that look nicer, okay? Okay, now, let's just switch it around. You don't have to, but I want to. All right, so x1, no. So a over 2vx squared, x1 squared plus v0y over vx times x. This is y1. All right. Why did I do all that work? Well, you'll see. Okay, so look at this in the parentheses. A is a constant. Vx is a constant. So this thing here is a constant, right? This is a constant. So I have y1 equals some constant times x1 squared. Now, v0y, where did that go? It's just some number, right? It's a constant, right? I mean, I don't know what it is, but it's a constant. Vx is a constant. So I have a different constant times x. Okay, now what is that? Okay, math people, should be all of you. What kind of equation is that? Y equals constant x squared plus constant x. What is that? That's a what? You better know this. It's a parabola, right? This is a parabola, you know? So here you go. So all we just did a special case, right? We did a special case where ax is 0, so no acceleration along the horizontal. The vertical acceleration is constant. Whatever it is, I don't care. And we just did the y versus x. And this is what we came up. Some constant times x squared plus a constant times x. This is just a parabola, right? Good old parabola. So what does that mean? Well, by the way, you can use that in a future lab. Okay? All right. Now, okay, so this is what we did, right? Ax is 0, ay is constant. We had that. And, you know, this could be a concave up parabola or a concave down parabola, right? If b is positive, it's a concave up parabola. If b is negative, it's concave down parabola. Now, let's say we switch. Let's say we have ax is constant for whatever reason, and ay is 0. Well, we know we're going to get the same similar result, but this time it's going to be x is by squared plus cy plus d. So if b is positive, concave or whatever to the right. If this is negative, to the left. Okay, but it's still a parabola, all right? So I don't care if you have ax 0, ay constant, or ax constant, ay 0. It's always going to be a parabola, right? And you'll see that's really important. You'll see in a minute. Okay, so here's a question for you. What is the trajectory, which always means y versus x, of a rocket launched with a constant vertical acceleration, a, from a railroad car rolling horizontally with a constant speed, right? So you have this car moving this way, constant speed, and while it's rolling, you shoot up a rocket, all right? So what's going to be the trajectory of that? So here it is. Everything you need is right there. So pause your video and figure it out. Okay, well, let's see. Horizontal motion is constant, so ax is 0, and ay is not 0. So we're back to this, right? We're back to this. Now, it says a is positive, right? A is positive. The acceleration is positive. So if the acceleration is positive, that means that this thing, right, is positive. Right here, okay? Okay, look at this has to be positive because it's something squared. So if a is positive, this constant here is positive. So if you have a positive times x squared, what's that? It's a concave up parabola, right? So basically, what would it look like? It would look like this. You know, the car's going like this. You shoot the rocket, it would go like this. Okay, that's what it would look like. All right, concave up parabola. Well, that's actually half a parabola, right? It's going to go like this, like I showed you, right? And you just see that from this, right? This is always squared. That's positive, so it's concave up. Simple as that, right? Okay, now what we want to do is we want to take an even more special case, right? So before, you know, we had this. We had ax is 0 and ay some kind of a constant. Well, now we want to make it a special constant. And I bet you can figure out what it is. What's the special constant going to be? Gravity, right? Gravity. So now what we want to do, we want to keep ax as 0, but now we want to say ay equals negative g, free fall, right? Ay is negative g, free fall, constant. So now everywhere where we used to have ay, there, and there, we're going to put in a minus g. So see in the blue, minus g, minus g, minus g. So these are called the free fall equations. But for whatever reason, they call it projectile motion in our book, okay? So projectile motion is like two-dimensional free fall, right? That's all. So, I mean, it's not so bad. You get your 3 kinematic equations plus 1 more. So, you know, rather than having 6, you have 4. So it's not so bad, right? Not so bad. So there you go. All right. So look at. So you have to memorize these two. But come on, you don't have to memorize anything new. I mean, agree? If you already know these 3, you know this. And if you know these 3, you're just putting in a minus g for the a. So really, is it anything new? Not at all. That's why it's so important to memorize those first 3. If you get the first 3, you get all of these. It's wonderful, you know. Totally, totally wonderful. All right, here's one of these pictures worth 1,000 words. I mean it. This is a very important diagram. So this is projectile motion, right? Free fall. First of all, what's the shape of the trajectory? It's a parabola. We just proved it, right? Okay, now, ax is 0, ay is negative g. So what do you notice about the horizontal velocity? So there's that. They're all the same. Well, of course they're all the same. Ax is 0, right? Now, ay is negative g, so it's going to get slower, but then faster, right? So what do you notice? So kind of fast, slower. Vy is 0, right? It's no longer going up. But then what do you notice? It's flipped. Vy is that. Then it goes faster and faster. So, you know, if you understand this graph, you got it. I mean, that's projectile motion. that truly, truly is projectile motion. So it's just wonderful. Okay, let's not. Let's quit. Okay.